Thank you, Professor, for such a brief and nice introduction. So, good afternoon, everyone. So, it is my pleasure to be here to present the today's seminar on the topic aerogels. So, the title is just advancing the aerogels from traditional to synthesis to modern multifunctional. So, here in today's seminar, I am going to introduce what I did the research of aerogels from traditional synthesis strategy to synthesize silica-based aerogel, traditional aerogels, conventional aerogel, and how we use another method I mean synthesize different kind of aerogels, not only silica. So that I will introduce briefly every research. Okay, so this is briefly about me. So I am basically from India. So this is my hometown, Kolhapur. Okay, so here, and the Kolhapur city is rich in its cultural heritage as well as history. And Kolhapur is famous for this non-vegetarian cuisine food, that is red curry and white curry, which is very famous in our state. And it is also famous in the world for this handcrafted leather shoes. Okay, we call it chappal. So it is famous for that also. So aerogel is one of the nanomaterials. So before starting exact about aerogel, so everyone knows that there are different kind of nanomaterial. Each nanomaterial has its own advantages, okay, due to its functionality. So there are different zero-dimensional, one-dimensional, two-dimensional, three-dimensional nanostructures are there. So one can synthesize each kind of metamaterial or nanomaterial in the form wherever we require that, in what application we are going to use that. So aerogel comes in three-dimensional category. It's three-dimensional porous material. It's like metal organic framework, you may know, MOF, COF. These are the highly used porous materials for catalysis application or gas storage applications. So similarly, aerogel is one of the porous material, three-dimensional porous material. So I'm going to introduce about aerogels. Okay. So it is the lightest solid in the world. So first reported by Jet Propulsion Laboratory in California, USA. Lightest solid. So light density is as low as 3 milligram per centimeter cube reported by them, that Jet Propulsion Laboratory. So one can synthesize aerogel in any form. So here you can see granule type aerogels, silica-based aerogel transparent. One can synthesize monolithic aerogels. Flexible polymer aerogels are there. Polyamide aerogels one can synthesize, and MTMS based or silane based flexible aerogels also you can synthesize. So this is the silica aerogels. First we synthesized by our Professor Rao, my PhD supervisor. It is first flexible aerogel, silica aerogel reported in aerogel.org website also. And one can synthesize graphene based or carbon based aerogels. So wherever we are going to use that material, we can synthesize. So briefly about the history of aerogel. So first aerogel was produced by Professor Samuel Kistler. He was doing some experiment with silica gel, and by accidentally he removed the fluid from that gel, and he obtained the three-dimensional solid network of silica only. So first aerogel paper is published in 1930 by Samuel Kistler in Nature, and first aerogel company started by the name of Sontocell product name in 1942 by Monsanto Corporation, but due to the cost required or necessary cost for the producing the aerogel materials, they stopped the production of the aerogel in 1970. But if we see the current scenario of aerogel market, so the global aerogel market will likely to reach around $1,000 million by 2026. It is increasing fastly, and there are key pioneer companies for aerogel production. They are commercializing the products, and the United States is a major global leader in terms of penetration of aerogel in oil gas industry as well as in insulation industry. So what are the aerogels basically? So the definition here gives us general view for silica aerogels, but every aerogel, if you remove the transparent word, you can define each case of aerogel. So aerogel is nothing but its lightest and transparent solid obtained from gel replacement of liquid component with air. So there is 3D gel type network. Suppose if you consider hydrogel, so we are removing the water or any solvent from that gel and just maintaining that 3D structure as it is. So that is aerogel. So there are different kind of aerogel one can synthesize. So basically silica aerogels are very famous because from last means we can say 90 years we are means using silica aerogel for different applications. Like its main advantage is thermal insulation. So it has a very low thermal conductivity, less than 0.02 watt per meter Kelvin. So very low thermal conductivity, near about air, we can say less than air also we can prepare. Density is very low, porosity is very high, so more than 90% you can achieve also. Dielectric constant is near about air, so 1.1 dielectric constant you can get. So that's why it has some beautiful, I mean, outstanding properties. So we can use this kind of aerogel materials for different applications. And this photograph is, we did some project for Cherenkov radiation detector. So we prepared some silica aerogels with central notch. So that can be used for high temperature at plasma state. So we prepared like this type of sample, aerosol sample also. Okay. So if you compare the properties of aerosols with dense silica, the silica aerosol has outstanding properties. If we compare, the density is very low in case of silica aerosol, porosity is very high as compared to dense silica, and the only property we are now focusing is mechanical properties, that is Young's modulus. Young's modulus of silica aerosol is most around 100, maximum 100 megapascal is achieved till now, and dense silica is in gigapascal. So we need to achieve high modulus, so that as per the NASA science news, we believe that aerogel can be used as much as plastic is using nowadays. So that is the intent of NASA. So NASA has a separate laboratory, Glenn Maxwell Research Laboratory for aerogel research. So they are also working on aerogel for different applications, space applications. So this is a basic synthesis process. If we go for a silica aerogel, so when we start for a silica aerogel, we need some organocylene based precursors like tetraethoxysilane or tetrapropoxylane, methyl trimethoxylane. These type of organocylene precursors we are using. And the main important thing is first formation of colloidal soul. So homogeneous colloidal soul should be formed, and that colloidal soul, that colloidal particles in the Brownian motion, they are always in a Brownian motion, they get connected with each other with some hydroxyl bonding. Okay, and that's why then you can get a wet gel after hydrolysis and condensation reactions. So at this stage you have to do use some catalyst to process the reaction, make it fast. Some acid base catalyst or acid or base catalyst you have to use. Then you can get wet gel. So wet gel is nothing but solvent is there, but the 3D structure of this particle connection, like pearl necklace like morphology, will get in the gel, that is in the wet part or water or any other solvent you can say. Mostly for TOS based aerogel, we are using alcohols, methanol or ethanol, lower alcohols. So you can see this is alcohol or water, blue part. So the main important thing is we can control the properties of the aerogel at this stage, formation of gel. So one can control the pore size, porosity or microstructural control at this stage. And that pore size, particle size or porosity can affect on the properties of aerogel after drying also. So if you want to achieve the transparent aerogel, you have to control the pore size and porosity of the aerogel. And finally, you can dry the aerogel using different techniques. So supercritical drying is one technique, and that I will explain detail in next slide. Ambient pressure drying is another technique. So at ambient temperature and ambient pressure, you can dry the aerogel. So mostly, if you consider the silica-based aerogels, like what I told, TUS-based silica aerogel, you need to, these are hydrophilic in nature. So that's why we need to modify the surface. So that surface modification is very important at ambient pressure, because there is a surface tension, high surface tension of the solvent at ambient pressure. So that's why there is a capillary stress. So to remove the capillary stress, we are using this supercritical drying method. At supercritical conditions, there is surface tension of the liquid is negligible, around zero, so almost zero. So that's why we can use this method, and we can get monolithic aerogel samples by using this synthesis technique. So this is a general reaction mechanism for organocylene-based silica aerogels. So hydrolysis and condensation reactions are mentioned here. And if we see, this is the autoclave we used earlier to synthesize supercritical dried silica aerogels. So it's high temperature, high pressure. Because if you use methanol as a solvent, the temperature goes almost, you need to around 265 degrees Celsius temperature, and almost more than 100 bar pressure is required. So it's like one atom bomb when you do the experiment with that. So you have to take care while doing the experiment. So at that condition, this surface tension component is negligible. That's why there is no capillary stress or capillary pressure, and you can achieve the monolithic without shrinkage or without crack, more than 98% porous aerogel material at that condition. And if we compare the ambient pressure drying and supercritical drying, the time period required is almost nearby same. But ambient pressure drying is a low cost method because we are not using any high cost instruments for that synthesis, and supercritical drying we need some high cost instrument to synthesize the aerogel. Yeah. So another methods. So when we consider the supercritical drying, so this is a phase diagram, pressure temperature. So you have to consider, you have to dry the sample at supercritical fluid state. So this is triple point. So at supercritical state, that fluid is easily, we can remove easily at that state because the surface tension of that fluid is negligible. So that is the condition. And another method is freeze drying also. You can directly freeze it and dry it. So you can also remove the solvent from that freeze drying condition also. So this is freeze drying general schematic here I provided. So while doing freeze drying, some people use copper plate. So copper is has high thermal conductivity, and that's why when we freeze the sample, we can get directional crystal formation, ice crystal formation. So if you want some directional porous structures, then you can use like this strategy, and you can dry the sample at freeze drying conditions. And then you can dry using a vacuum, then you can totally remove the solvent. And recently, many people are using this additive manufacturing or 3D printing. So in case of aerogel also they are using, but in this case, the formation of ink and the velocity of, viscosity of ink is very much important when we try to additive manufacture the aerogel. And finally, you have to use some supercritical drying process. So this supercritical CO2 drying process is good because CO2 is not that much harmful, and temperature we required at supercritical state for CO2 is around 40 degrees Celsius. Pressure we can go more than 90 bar, 95 bar. So that is we can use supercritical CO2 drying process instead of supercritical alcohol drying process also to synthesize the aerogel. When we consider the hydrophobicity of the aerogel, this is just general concept. So hydrophilic aerogel is nothing but it can absorb the water totally, because on the surface of silica aerogel, normal silica aerogel, maximum OH groups are there. So OH groups can attract the water molecules, so you can get hydrophilic nature. So to long last the aerogel, or to use the aerogel for commercial purpose for long duration or increase the durability, you need to make the surface hydrophobic. So that's why we are using some methoxy group containing precursors, organic precursor, to modify the surface so they can be non-polar to water. So that's why the water will bedded on the surface. So your sample will float on the water surface. So that is hydrophobic aerogel. And one important thing, characterization or this property of aerogel, thermal conductivity. So what is thermal insulation? So heat transfer in aerogel. So generally we know the heat transfer can be possible by conduction, convection, and radiation. So solid conduction is negligible in case of aerogel because less than 10% solid network is there. So solid conduction is negligible. So this part will almost less than 10%, we can say. And gas convection is another part of heat flow. But in aerogel, the pore size is less than 100 nanometer. So mesoporous aerogels generally if you can consider. So which is nearby the mean free path of air, 70 nanometers. So that's why this gaseous convection of thermal conductivity or heat is lower in case of aerogel. And last part, this part can be considered when we go at high temperature, infrared radiation. So infrared radiation always increases the thermal conductivity of aerogel at higher temperature. So that infrared radiation, radiative part of thermal conductivity can be reduced by using some opacifiers, which can block the infrared radiation and just decreases the thermal conductivity of aerogel at high temperature. So we did some work in 2017, and we just theoretically calculated the radiative part of the thermal conductivity in case of silica aerogel. So we use some yttrium oxide powder as opacifier in silica aerogel, and we opacified it. And it is found that when we opacify it using some powder, opacified powder, the radiative part decrease, and that radiative part can affect on decreasing the thermal conductivity at high temperatures. So this small decrease in thermal conductivity is also helpful when we consider the aerogel for means high temperature application. There are different multidimensional aerogels. So one can synthesize aerogel, I already told, in any form. So one can synthesize particulate or colloidal based aerogels. So this is mostly silica based aerogel or metal oxide based aerogel. So this is pearl necklace morphology. You can get connection of particles. Okay. One can synthesize polymer aerogels also. So fibril-like network, mostly polyamide aerogels, you can see polyurethane, you can get fibril-like network, polymerized network. And nanofibers or nanoparticles, you can disperse and you can use freeze dyeing concept, and one can synthesize fiber type aerogels. So knotted structure you can observe. So there are connection between the fibers you can observe by using this type of synthesis. And we can also synthesize the two-dimensional sheet-based aerogels. So two-dimensional sheet, just we need to disperse, and we can use some freeze dyeing concept, and we can form this type of 3D network foams of aerogels by using this. And these are the materials we developed till now. So different kind of aerogels we worked. We prepared carbon-based aerogels, polymer-based aerogels, transparent silica-based aerogels with higher modulus. And we achieved the modulus is around 1 gigapascal for carbon aerogels, what we prepared till now. And so generally, just briefly, I will discuss my work, what we did, just briefly. So this is first work, what I did in 2018. So just we tuned the molar ratio between solvent and precursor. So here I use tetrapropyl propoxysilane as a precursor first time. And just by tuning the molar ratio between this methanol and TPUS, we can change the porosity and transparency of the aerogel. So you can see this lower molar ratio means between the precursor and solvent, it gives us a dense network, dense structure. So that's why you can see the opaque aerogel. And if you can increase the molar ratio between solvent and precursor, you can get highly porous network. So it is highly transparent aerogel. So this we synthesized at ambient conditions, ambient pressure, so modified with some TMCS, that is trimethyl chlorosilane silylating agent, and it got some hydrophobicity, higher hydrophobicity as compared to pure silica aerogels. Okay, in this work, we use some co-precursor. So co-precursor method is nothing but we use some silica-based co-precursor to modify the surface. So this is also good technique to modify the silica aerogels to increase the mechanical properties. So basically the silica network, it has some hydrolytic group on the surface. So we can cross-link this that silica precursor, you can say 3-trimethoxyl propyl methacrylate, PMSPM we can say, and we just get some cross-linked silica network. So this surface contains some acrylate groups, and that can enhance the modulus of the aerogel, you can see. So modulus increases when we increase the percentage of TMSPM in silica aerogel, and thermal stability also increase because of the acrylate group on the surface. And we achieved the hydrophobic aerogel after this modification, because pure pristine aerogel is hydrophilic, so it gets settled down in the water. But Ormosil aerogel, what we prepared, organically modified aerogel, it sustains on the water surface. So hydrophobic one. Another first time we synthesized silica aerogel films. So very highly porous, nanoporous films we synthesize by using this technique. We use some epoxy amine cross-linking. So we use some epoxy group containing silica precursor and amine group containing silica precursor, APTS and GPTMS, and we did just epoxy amine cross-linking, and we got some cross-linked aerogels. And these aerogel films we prepared, this was the Samsung project for low K dielectric we did, and we achieved good results. We got a low K value around 1.7, so which is lower value we achieved. And for that, we use this type of technique, ring opening polymerization, and that's why it gives GPTMS is act like a binder, so it binds strongly with the substrate. So we use silicon vapor to coat the aerogel samples, and we achieved these results for that project. Again, we did amine modified. So amine groups are very good to capture the CO2. Okay, maximum CO2 they can capture. So carbon dioxide capture and heavy metal removal, we did this study, and we just use normal silica precursor, and we compared with APTS modified silica. So this material gives us a good result because it has on surface, the amine groups are there. It has high affinity with the carbon dioxide, so that's why they can capture. So we use this material for CO2 gas selectivity and adsorption, as well as heavy metal removal. So you can see mercury and lead removal is possible by using this type of amine modified silica aerogels. Again, we first time we synthesize these aerogels. So this is a silica nanofiber aerogel. So in this synthesis, what we did, generally people are doing preparing first nanofiber mats, and they are immersing that in the sole, and they are preparing composite of aerogel. But here we got in situ aerogels by starting with synthesis of fiber. We ended with aerogel synthesis, three-dimensional aerogel synthesis. That is our technique. So in that case, we use silica precursor, that is TUF, what we are working now. So at changing temperature, aging temperature, you can see the growth of fiber. So first, it is in nanoparticle form, colloidal particle, then it forms the capsules or bullets type structure, you can see. And then after aging at some time and some more time at certain temperatures, we optimize that at 85 degrees Celsius, it forms higher length nanofibers, around 11 micron length we achieved for one fiber, with diameter, you can thickness is around 100 nanometer, less than 100 nanometer we achieved for this type of material. So this is the data with respect to time and with respect to temperature, how we got the change in diameter and change in length of the material. And this we use to synthesize aerogels. So directly in situ, we use that fiber solution with the aerogel, and we achieved the aerogel. So this TM images proves that this is ex situ aerogel fiber connection and in situ. So in situ aerogel fiber connection, you see the thin aerogel layer with silica nanofiber particles layer is possible. But if you use ex situ, just prepare first fiber and immerse in the sole of silica, agglomeration of aerogels. So there are many aerogel particles connected. So there are connections, non-connections are possible when we use ex situ approach. So that's why we adopted in situ method. And that materials we use for thermal insulation. So this is our student. We did some experiments. So he has aerogel samples with him, and at noon time we check the IR images, change in temperature. You can see this is the normal temperature, and if you put the aerosol sample, this is the temperature difference. Here also same with hand. So here you can see the change in temperature difference you can find here. This is normal temperature and change in temperature. So that, and in the night time also we studied this. So change in temperature when we use the aerosol samples. So that's the beauty of aerosol. It has low thermal conductivity, and you can use that aerosol samples in the cloths for winter time or high temperature summer time. As our firefighters also can use this type of materials as insulating materials. This technique also we developed with Professor Kanamori. We worked, and we achieved this type of transparent and flexible aerosols by using PMSQ, that is methyl MTMS as a precursor we use, and we prepared this kind of aerosols with Professor Kanamori from Kyoto University. Another interesting result we got from inotropically cross-linked. So here we use sodium alginate. Okay, it cross-linked with the silica, and first the process we use as a post-gelation. So while first we prepare the TUS gel, and then we modify the surface with sodium alginate solution, and then we cross-link it with some ionic cross-linking, and then also we prepare these samples. And these aerogels have an interesting property because there is a sodium alginate, and which is very good for dye adsorption, and with the aerogel has a high surface area. So we use this material for selective dye adsorption, water treatment. So we achieved good results for in case of selective dye adsorptions. And you can see your filter. This is a dye solution, methylene blue dye solution. But this is here is the aerogel, and with aerogel you can see we can separate the water and aerogel. So filter, it works like a filter. So from UV visible data you can find here that this is for methylene blue. So and if we filter it, so the curve is you can see zero at the zero line. So that is highly transparent. Means you can purify 100% water from that MB solution. So that is the beauty of these aerogels. Another thing we did, that is titania silica. So these are the composite aerogels we did. So here also we use same approach epoxyamine, but we use some titanium based precursor with MTMS as a hydrophobic silica precursor, and we did epoxyamine cross linking, and we achieved crystalline titania at supercritical condition 265 degrees Celsius. We achieved anatase phase for titanium oxide, and that is good for photocatalytic dye degradation. And we did photocatalytic dye degradation by using these samples, and it means removes 87% methylene blue after 1 hour 30 minutes of exposure with UV light. Here also we use some porous foam, carbon foam, conducting foam, because mostly if we use titanium or tin oxide aerosol, they are in the powder form. The dimensional network is there, but they are in powder form. So when you use for photocatalytic application, uh, removing powder is very difficult. So for that purpose, we did this study with some conducting foam, carbon foam, which has in the role in the adsorption. But we coated the titania aerosol on the surface, also on the onto the pores of this carbon foam, and we use that for rhodamin B dye degradation, and it shows good efficiency of rhodamin B dye degradation. And also we use some tin oxide aerogels. But when we consider titania aerogel, we use sol-gel process. But when we use other metal oxides like tin oxide, iron oxide, or any other metal oxide, in that case, you have to use this synthesis process, epoxide initiated gelation, because there is no, we can't use the sol-gel process because we are using salt-based precursors for this kind of aerogels. So when we use chloride-based or salt-based precursors, we have to use the epoxides to means epoxide ring opening polymerization also happens here. So some epoxide you have to use which can initiate the gelation of this kind of precursors, and then you can achieve this kind of 3D network for these metal oxides. So that is another approach. We did this project with Hyundai, and we use peelable coating. So most of the people, the X-peel, because when there are new cars, there is a plastic covered on the car. That is not a plastic. Okay, this is the paint. Okay, that is a peelable paint. We can say X-peel. So that paint we can remove because after drying, after painting, it can dry and it can become plastic. So that we can remove easily. To that purpose, the X-peel is there. This peelable paint. So in that case, we want to decrease the TZ value of this peelable paint and increase the flame retardancy of the paint. So we achieved that by using our magnesium hydroxide silica composite aerogel. So we immersed magnesium hydroxide while synthesizing silica aerogels. It is good for flame retardancy. And if we compare here, this is a original detachable coating X-peel product what we got from the company, and this is not that much bendable. It is very thin, and it can catch fire at within a second. That is the disadvantage of that, and that we removed. We used some MgOH2 silica composite aerogel, and we achieved high bendability, so mechanical strength for the peelable coating, and also we achieved good flame retardancy. So it is not flammable for a long time, we can see from this photograph. So that result we obtained from this data. Another work we did is polyamide maxine crosslink, nano crosslink aerogels. So in that case, we prepared polyamide aerogels comparison. So that polyamide aerogels are, so we want to increase some mechanical strength and thermal stability of the aerogel or flame retardancy of the aerogel. So we added maxine sheets, nano sheets in the aerogel, and we got polyamide maxine cross-linked aerogels. So this is a polyamide aerogel. You can see fibril-like structure, porous structure, and maxine cross-linked. You can see maxine sheets. In the TM, you can observe that the fibers connected with the sheets of the maxine polyamide aerogels. So we use for high temperature insulation and cold temperature insulation. So this we studied by IR camera, and we use butane torch. The temperature is around 1300 degrees Celsius, 1300 degrees Celsius. And you can see here polyamide aerogel. In case of polyamide aerogel, after 1 minute, it can get separated into granules. Okay, after 1 minute. But if you can modify it maxine, it can sustain for a long time. So 15 minutes also, you can find that just little shrinkage in the material, but the monolithicity is as it is. So that is the advantage of addition of mixing, because it has some titanium carbide groups, so it can sustain for that temperature for longer time. And also we did cold temperature insulation, so we use some copper plate, and on the copper plate we use some water beaker, and here is the aerogel, and on that surface also we kept water beaker. And if you can find up to 30 minutes, this water beaker, only water beaker has formed some ice crystals, but the aerogel surface water means that beaker, you can't see the formation of ice. So that is the insulation property of that aerogel. So we can use for cold insulation also. This work is under processing. So this is also interesting work we achieved. So we are working presently. We prepared some polymer, RF polymer based aerosol, resorcinol formaldehyde, and we use some epoxythiol cross-linking. So that epoxythiol cross-linking gives us the thickening of this neck. So you can find in from these TEM images, when this is for ambient pressure drying material. So mostly for ambient pressure drying material, you can see the agglomeration of particles, because we are drying the aerogel at ambient state. But if you can use some supercritical drying methods, you can see highly porous, mesoporous network. And we compared with conventional aerogel. This is a conventional traditional aerogel synthesis process, reported process, and this is our process. So you can find that neck thickening is possible. The connection between that two particles between the aerogel is enhanced, and that's why we achieved a high mechanical strength in thick necked aerogel, this kind of aerogel. And we measured the mechanical properties for this. It is, you can find the interesting result. The ambient pressure drying aerogels are strong, okay, because it has a like a zero gel. It is like glass, so it is strong. You can find from pore structure. And the traditional aerogel, they use some APTS as a gelating agent, so that are weak, we compared, but our aerogels are strong but flexible. So it is stronger as well as it has a flexible properties. So you can see the cyclic curves of mechanical properties at different compression strain. So at almost up to 50% strain, it is stable. So we can compress that material 50%, and it can again regain its original dimensions up to 50% with some few percent miss loss in the dimension. So you can find, we did cyclability study also till 100 cycles. We studied this to determine the friction means energy loss coefficient and maximum stress. We can see it is nearby constant after some cycles. Okay, and this coefficient also constant after 50 cycles. You can see it is stable 0.4. And if we compare the modulus data, mechanical modulus, Young's modulus, with other reported results, we achieved 5.65 megapascal mechanical strength for this kind of aerogel, so which is higher as compared to other materials. And we use this material because of its functionality. It has some epoxythiol groups and some polymers, so we use for heavy metal adsorption and dye adsorption, and it shows a good adsorption property. So maximum adsorption coefficients are mentioned here for heavy metal. So it absorbs mercury, so you can see the, we also did selectivity, so it absorbs maximum mercury, so which is very heavy metal and very dangerous. So for health. So we got this nice result from this data. And yeah, next study is same RF aerogels. We converted into carbon aerogels, but the process is different. Just we tune the molar ratio between water and the precursor, what we use here, and we found that we achieve some sphenoidal decomposition phenomena, and we achieve some hierarchical porous aerogels. So you can see the images of the pure RF aerogel, polymer aerogel after carbonization in the nitrogen atmosphere. You can found these carbon aerogels. So highly conducting aerogels we can achieve by this, and the shrinkage is not that much. From photo we can easily see that, because most of the carbon aerogels shrink a lot. And we measured the surface area is almost 88 meters square per gram, and it has some micropore and mesopores. So that's why we mentioned it as a hierarchical porous material. And if you can see the conductivity, electrical conductivity, so the second sample, it got higher electrical conductivity because of its hierarchical pores and high concentration of material network of carbon in that. So it got higher electrical conductivity as compared to other materials. And these materials we use for supercapacitor application as well as EMI shielding application. So for EMI shielding, you can see here directly, this is the bare watch. You can see And from that, there is no any EMI shielding. And if you use paper, still it is working. But if you use aerosol, same size aerosol, here you can see watch will not turn. So that is EMI shielding experiment we did with this kind of aerosols. So this work is also in under process. Another work we use the material for aerogels for electrocatalysis, which is a normal energy conversion approach nowadays people are working. So this work we published in ACIS Nano, and here we prepare tin oxide aerogels, fluorine doped tin oxide aerogel modified with platinum. So we use sputtering technique to atomically disperse the platinum on the surface of the aerogel, and this platinum modified tin oxide aerogel can achieve higher hydrogen evaluation reaction potential. Okay, so lower potential, lower potential. That potential is mentioned here. It is around 40. So that is comparable with the previously reported results. So very low over potential we obtained for that sample. This another synthesis approach we use here, the assembly approach, self-assembly approach. So to self-assemble the aerogels, we use some mercaptosacinic acid. And by using that mercaptosacinic acid, we prepared some sulfide-based or chalconite-based aerogels. But we can tune the morphology of the aerogel by adding some DMF and formamide in that. So these are some gelating agents, we can say. They can tune the morphology. So we can prepare zero-dimensional and one-dimensional aerogel. So you can see one-dimensional aerogel, highly fibrous aerogel, so connected aerogel. So we can see knotted aerogels like this. And these are zero-dimensional aerogels. And we use that for supercapacitors. So I will not extend a lot on the supercapacitor, but we use for supercapacitor, it shows good supercapacitor performance. Again, similar strategy, we use some graphene with this cobalt sulfide, and we assemble that sheets and fiber together. And if you can see here, the cobalt sulfide has highly fibrous structure, okay, and that we come cross-link with the graphene sheets. So that graphene with cobalt sulfide can be useful for lithium-ion battery application. So we use that material for lithium-ion battery application. So you can see that we can synthesize some fibrous aerogels by using this kind of strategy. Here also, we prepared some ligand orchestrated aerogels. So we added some ligand with the reported process, and we just changing the concentration. So high cobalt content, you can get this entropy, medium entropy oxides, sulfur oxides. You can see iron, nickel, cobalt. This is nickel centered, and when low cobalt, you can get some cobalt centered sulfur coordination. And this type of morphology, tip-like morphology, this gives us a better performance in oxygen evaluation reaction. So the over potential is as low as 190 millivolt, around 190 millivolt we achieved by using this kind of material. This is also beautiful. So we use this same mercaptosacinic acid, and we connected the carbonitride sheets as a 3D connection. And the surface, there is nickel cobalt sulfide aerogel. So from EDS mapping, you can see that homogeneous formation of material, the carbon nitride as well as nickel cobalt sulfide on the surface of the aerosol. And this we have used in supercapacitor as well as HROER reactions. And this is last work. What we did, you prepare some nickel iron tin oxyhydroxide. So this is the first work. We use some wet gel. So without forming directly aerosol, because generally what we do, we prepare aerosol and then we prepare electrodes for electrochemical measurement by using powder and binder. So without using a binder, just we use some nickel foams or collectors, current collectors, and we coated the samples on that current collectors. And here you can see we tuned the crystal structure, because when we use some amount of tin, it goes to the amorphous phase, because the quantity of tin is very much important when we use. And tin oxide mostly goes in the foam type structure, oxide foams. So that's why we are choose the amorphous nature. But still, this material shows a good HROER performance and water splitting ability. So you can see the porous aerosol network here and crystallinity of the material. It is amorphous mostly. And you can see it is stable for longer time. 70-hour experiment we did water splitting, overall water splitting, and we achieved 1.55 volt overall water splitting potential for HFOAR for this kind of material. Yeah, so this is there are some recent trends briefly I want to share. So this we did in our review advanced material we published. So you can see here, sorry, there are different methods we can use to synthesize the aerogel. One can synthesize a hierarchically porous aerogel, 3D printed aerogel, and aerogel fibers. So in all, you can see common same materials, but different structures. So this is the beauty of aerogel work. So you can synthesize any type of morphology in the aerogel with any kind of network. So aerogel fibers, so one can say this is a knotted aerogels. So you can prepare aerogel knots also. You can prepare aerogel fibers, and we can prepare a knot. So different, so this structure, you can see this porous structure is inside the fiber. So suppose this is the fiber. So in the fiber, you can see this type of morphology. Okay. So that type of aerogel fibers one can synthesize by using electrospinning technique or sol-gel spinning technique. So these are some same materials, but different type of structures we can synthesize. And the overview is that you can prepare any kind of aerogel, just you have to use some most suitable strategy to synthesize that aerogel. There are different strategies to prepare the gel, and the present scenario is we have to use some different dimensions. So you have to prepare 0D, 1D, 0D, 2D, 1D, 2D. So depend on which type of application. So you can prepare multi-compositional, multifunctional aerogel and multi-dimensional aerogel by using this kind of different strategies, tuning the or playing with the sol-gel reaction or solution with of aerogel. You can prepare any kind of aerogel. So knotted chiral metamaterial, what I say, if we can say aerogel, so we can synthesize aerogel as a knotted chiral metamaterial. So as we mentioned in our review, aerogel can become the future material for Mars colonization. So with Professor Kamamori, we work on this, and we can see that on Mars, there are different minerals. So how if we prepare the aerogels from that minerals? So if you want to use the material for future colonization, how we can synthesize the aerogels on the same minerals? So that is the thing. So I am presently working to synthesize clay-based aerogels here using ambient conditions. So presently in the starting part, so I'm working on these materials. And you can also synthesize chiral nematic aerogels using cellulose nanocrystals. Okay, so you can arrange the chirality. So you can use anisotropic and isotropic cellulose nanocrystals, and you can arrange that material by using freezing technique. So you can get directional mechanical properties and thermal conductivity, surface dependent. So if you want that type of material for different applications, we can synthesize that type of aerogels, and we can also consider knotted aerogels. So aerogel fibers or aerogel knots are at the nano level. You can find the knots in the aerogel microstructure also. Okay, so these are some collaborators. I would like to thank my collaborators because they helped me a lot for the experiment and collaborations. And thank you very much. So presently I'm working as an editorial board member for various journals. You are welcome for your future submissions to these journals. Thank you. Yeah, thank you very much.